with redshift, yeah, the way to explain it best is if you imagine an object or a vehicle or whatever it may be, a source of light or sound waves, even, right? But in this case, we're dealing with sound waves. So imagine you've got a body, right? It could be anything, but in this case, we are talking about planets and stars and galaxies, that sort of thing. Okay, so it's there, fine. It emits light, so electromagnetic waves, right? And let's say in one period of time, that light travels that far. So that could be like 1 second, maybe, right? And so every second, we'll deal in units of seconds here. So every second, it's sending out waves, which, if it were stationary, they would work like this, right? So, and so imagine that is 3 seconds, this one is 2 seconds, and that's 1 second, all right? So that's what it would look like if the waves were just going out in a spherical way, right, around the object in every direction, okay, for a stationary object. Okay. Now, what happens in reality if that object is then moving? Okay. So if we take a similar kind of a setup, and this is a bit that actually is, I don't know, a little bit difficult, but I'm going to try and do this. So imagine the first one is emitted here, right?
Yeah.
And so the wave, let's say 3 seconds later, as we've already seen, is already there, right? It's traveled there. A little bit later, the object is moving in this direction, let's say, in that direction, okay? A little bit later, it then emits a wave, okay, which, let me put that there. Okay. So that's going to be about half of the two. So, yeah, all right. I'm going to try and do it there. Like that, all right? So this is the first one, like that. Then the second one, all right? Then the third one, like that, okay? What effectively this means is, as the object is moving in that direction, it's catching up with its own emitted waves. All right, does that make sense?
Yeah.
Yeah. So the next wave that's emitted, right, in the time it travels forward, like this, okay, it's actually catching up. The wave fronts are catching each other up, right? Now, admittedly, the diagram could be a little bit better, but freehand, I suppose, is the best I can do. So now, imagine that you are standing at A or at B, okay? The person at B, so if you're an observer at B, right, what you're seeing is that the wavelengths are shorter. Do you see? Yeah? So the wave fronts are hitting you more frequently. Therefore, the wavelengths are actually shorter. All right. That makes, so on this side, observed, that's the important thing. The actual wavelength is not shorter, but the observed wavelength is shorter. Does that concept make sense?
Yeah.
All right. So observed wavelength, okay, is shorter. wavefronts catch up, as it were, with each other, or previous ones. All right? Okay. Now, if the wavelength is shorter, remember on the electromagnetic spectrum, right?
Yeah.
Okay. What you have is short. Oh, sorry. What am I going to do? This is the long wavelength,
Yeah.
right? And on this side, you've got the short wavelength, right? And the visible light spectrum, okay, is like this in the middle. Yeah? Now, do you remember which side, right or left? Which side is red and which side is blue?
I think right is red.
Nope, the other way. Okay?
Okay.
That's infrared and that's blue, ultraviolet.
Oh yeah, I read that, but like my side, so
Yeah, but this is long, so
yeah.
infrared is actually the longer wavelength. Okay?
Yeah.
So
Yeah.
this is the red end and this is the blue end. Okay? All right. So what that means is, going back to this, if the wavefronts catch up with previous ones, the observed wavelength is shorter. Right. So if it's going towards a shorter end, then you get blue shift. Okay? So there's blue shift. And if you have it going to the longer end, that's red shift. Okay? So in this case, what happens is B observes shorter wavelengths, right? So if you're in front of the object is approaching you, you get blue shift. Okay? Whereas if you're behind, and I'm going to put it there, right? A observes longer wavelength, right? So as far as A is concerned, the wavelengths are getting longer, right? Appear to get longer, right? And therefore, that gives you redshift.
Okay.
Okay? Does that now make sense, the concept?
Yeah.
Yeah? All right. So the rules are as follows. If an object is moving away, right? Then you have wavelength of observed light appears, all right? Appears longer. Okay?
Yeah.
As a result, the light seems to be bluer. So again, it appears more blue than expected. Oh, what am I saying? Let's correct that. meant to say red. Okay. Red, right? So let's correct that. Light appears more red than expected. Okay.
Yeah.
And how red it is tells us the speed at which the, call it star, etc., is moving away. Okay? All right. And vice versa. So opposite, exactly opposite for blue shift. Okay? All right. Now, the significance of all of this is that this tells us universe is doing what?
Is expanding.
Exactly. Tells us universe is expanding. Okay. So for example, if that's planet Earth, all right, and you have a star somewhere like that, and it's going away, all right, and another star here, for example, going away, right? So if everything appears to be more red, all right, than it's supposed to, then it means everything is moving away and things are getting further apart, right? So that is the evidence for expansion. Does that all make sense?
Yeah.
Yeah? Any questions on that?
No.
No? And you're okay with the diagram?
Yep.
You see how the difference is between stationary and the one that's actually moving. Yeah? So this is moving. I better put that in. Okay? All right, cool. Stop there.